got job offers from Google, Meta, Amazon, and Uber without a computer science degree. Here is how I prepare. I got job offers. I got job offers from Google, Meta, Amazon, and Uber without a computer science degree. Here is how I prepared for system design interviews. I started with Professor giving my last lecture on scalability. This video covers basics like horizontal scaling, load balancing, and security. It also covers slightly advanced concepts like data partitioning and security. Next, I wanted to learn more about the architecture of some real-world use cases. So I did this course called Rocking the System designed by Educator. This course covers the design of systems like Newsfeed, Webcrawler, and Uber. After doing all that, I felt confident enough to read engineering blogs. Many tech companies have blogs where they share learnings from scaling their systems. Some of the blogs that I read were Netflix tech blog and Uber's engineering blog. I got job offers from Google, Meta, Amazon, and Uber without a computer science degree. Here is
Hi everyone, my name is Anu, and in this video I want to talk about how to clear my system design interviews at Bloomberg, Atlassian, etc. So in this video I'm going to share all
When I first started to do software interviews, when I first started to do software interviews and I was asked to do system design interviews, I looked online for all kinds of different ways to find a systematic way to study. For lead code, it was like go through this list, go through that list, learn this data structure algorithm. But for system design, there didn't seem to be a specific way that people study. I took that as heart, and a lot of times in my past interview experiences, I would leave system design as something that I was just winging on the interview. The interview would come and I would just start to like make shit up and then hope that it would work out. But based on my experience, system design is one of those things that you really either know it or you don't. An interviewer is kind of going to know if you know what you're talking about or if you're just making things up because you don't know what you're doing. So today, I want to take what I learned over the past couple months and the past years of me interviewing myself and try to explain my own process for studying system design now. So let's start with active learning. Okay, to start with what I've done in the past. The way I studied system design in the past was I used this system design primer GitHub repo. This is posted all over Reddit and I'll post it in the comments down below or in the comments section, the description, sorry. But basically this is a gigantic README doc that is pushed to GitHub that explains every little system design nuance you could possibly think of. And this works very well. There's a whole bunch of papers that links to and a whole bunch of different links and blogs and everything like that. This is an excellent tool for you to use to study system design. But the thing about it is that people learn slightly differently based on who they are. And for me, reading things, I just learn very, very slowly and it's difficult for me to grasp a lot of information. So I use this more as just one of my sources. The source I've been using most commonly in the past couple of months is a YouTube channel called Jordan Has No Life. This guy basically has made a whole bunch of videos about the system design basics like described in the earlier GitHub repository I was talking about, but he's also made a ton of videos about designing all kinds of different systems. And the thing about his videos is that he is super in-depth, more in-depth than I've seen pretty much any YouTuber out there go, where he'll take a problem and he'll really, really drill down into what happens and why it happens. The most obvious example probably is when he talks about database indexes. I don't want to play too much of it, but basically he goes very deep into how the database actually stores the data, how it actually does everything behind the scenes, like what types of data structures are using. It basically shows you that a lot of system design and how technology is built out there isn't magic. Like things behind the scenes don't just run because there's some sort of crazy algorithm behind there. They're all just data structures and algorithms, just like we learned in all the computer science classes. So if you're a person who really likes to watch videos to learn your information and to learn how to study, I would recommend you check out this YouTube channel, which basically he has a whole set of videos for every single small piece of the system design puzzle that you need for interviews. He's got like 60 or so videos. I watched all of them. They're great. And then he has about like 30 or so videos just designing very common systems that we use on daily basis, like Facebook, Instagram, Twitch, stuff like that, Discord. And when you're watching the videos, it can be really easy to feel like you're being very productive. Like you sat here for an hour watching the video and you feel really good about yourself. But the thing about it is, if you don't take notes and review them in a careful way, you can be very easily kind of wasting your time a little bit. A lot of times when I studied system design in the past, I never really took a lot of effort to take notes. I would just look at things and then be like, okay, I got it, and move on. So I designed myself a pretty systematic way of taking notes, which I will talk about later. And the last system design interview tool that I use is called Rocking the System Design Interview, which is also kind of a meme on Reddit and other sources and things like that. But objectively, it's a very good resource. It does one thing that the videos and the other GitHub repo that I showed does not do, which is it gives you a systematic way on how to actually interview in system design, how to break down your questions in a way where your interviewer won't be confused, which is where I move into the next section for practicing. So in real life, when you're doing a system design interview, you're working with a real person who's asking questions back and forth, you're trying to pick apart your design, you're trying to see how you would optimize certain things. So it's more of a conversation with someone. And this is where this Rocking System Design interview comes into play for me. Basically, what it does really well is give you a step-by-step guide on how to talk to interviewers. Right? Like step one, you clarify requirements with your interviewer, just make sure you're understanding the scale and scope and kinds of things you're going to be designing for your project. Step two is back at the envelope estimation, where you're trying to estimate like network bandwidth, you're trying to estimate like how much you need for caching, how much storage you need for disk memory, how many machines you might need to determine the true scale of your system. The third step is always like API design, basic stuff just to show what are the inputs and outputs for your system. The fourth step is defining a data model, which is basically like how data in your database is going to work and how it's going to be laid out. And the fifth step is like a high-level design where you just draw your whole application and the general places where all the little components of your system will be, which will show your interviewer from all these steps that you generally know what you're talking about. And then it has a sixth and seventh step, which is it's hard to really quantify in like a online tutorial course or something like that. But this is basically where in a real interview, interviewer will ask you questions about how you optimize it. or like how would you do this in a different way, or like why did you choose this for your solution instead of this other thing. So given that whole template, I mentioned earlier that I'm using different sources to actively learn, but then applying those concepts and practicing them are just as important, if not more important. What I do with this is I use that format that I just talked about, and then I essentially quiz myself, right? Like I go through these things, I look what the requirements are, and then I try to draw it out myself as if I'm testing myself. Like I'm doing the back of the napkin math in order to estimate capacity, which, side note, if you're like me and you're really bad at mental math, this shit was actually, it's way harder than you expect. It took me a while to completely understand it. But anyways, I calculate back of the napkin math, I quiz myself to see if it's right, or if my scale is right. I'll design the APIs myself and then quiz myself by checking, okay, are they right? Like, did I have the right idea here? I'll design my own database model and then kind of look at the database model here and see, okay, like, does this kind of match up? Like, what am I missing and why did I miss it? And then from there, I try to draw my own system architecture, the whole, drawing with all the components linked together, and try to figure out places that are bottlenecks, like things that can be improved. And then I come to this final section right here, which is where they have all kinds of different questions and answers. I generally just try to look at the old ones and see, like, okay, so what are the different issues of resolution, or like, can concurrency cause problems? Like, what would the DB key size be? Basically, I'm just pretending that an interviewer is asking these questions, and I try to fix, optimize, or at least understand what I did wrong with the final solution. Okay, so the final step of what I've been doing study system design is reviewing very, very consistently. I mentioned earlier that when you're learning, especially if you're watching videos or reading a lot of text, it's important to make sure that you're recording everything that you're doing. So for me, I'm a Notion nerd, as you might know, and I basically created this Notion database using the active recall format. If you watch my LeetCode video, you probably know that I love the active recall format, which is basically, as I'm watching these videos, as I'm like reading this stuff right here, I'm trying to constantly ask myself questions. Like I'm trying to ask myself, like, how does this little component work? Or like, what would I need for this other thing? Or why would I use this component over this component? Stuff like that. And I basically write all these questions down and I tag them by the topic specifically. So first I did it by topic, like while I was learning these system design concepts, I went through all those videos from earlier that I showed you, and I would ask myself, like, okay, what is it from this video that I could ask myself later to review? Something that I don't really know that well. So just playing a random example, if we're gonna look at caching, I'll write the question, explain, write back cache. And while I'm reviewing, I'll cover up the answer. And this is where I will try to explain it for myself. I'll try to look at the question only and then try to put the answer in my own terms. And then if I really can't get it, then I just look over the answer and read back to myself, okay, so what did I write before and what did I get wrong? At which point, if I struggle with the concept, then I will make sure to mark down as a question that I need to review and something that I struggle with more. So I have this checkbox right here in the same database for me to do that. I know all this stuff is a lot of work, but generally, if we just learn actively, at which point, if I struggle with the concept, then I will make sure to mark down as a question. At which point, if did I write before and what I just look over the answer and read back to myself, okay, so what did I write before and what then I will make sure to mark down as a question that I need to review and something that I struggle with more. So I have this checkbox right here in the same database for me to do that. I know all this stuff is is a lot of work, but generally, if we just learn actively, we take notes with the active recall method, and we practice system design over and over.
System design is becoming more and more common in software engineering. System design is becoming more and more common in software engineering interviews, even for people with 0 years of experience. But many people struggle when it comes to learning system design. Don't worry, in this video, I will share everything you need to know to master system design using freely available resources on the internet, even if you are a complete beginner. Just so you know, I currently work as SG2 at Amazon. After learning system design, I managed to land high-paying senior roles at several companies including Amazon, Microsoft, and Adobe. Today, I will talk about what system design exactly is, what concepts you need to learn, how to get ready for interviews. Most commonly are system design interview questions, and what is expected in a system design interview. So let's get into it. What exactly is system design? System design isn't about writing code, it's about the big picture. It is based on the principles of distributed systems. A distributed system is a group of computers working together to achieve a common goal. Group of computers can handle more data, serve more users, and do tougher tasks than one computer alone. System design involves figuring out what are the requirements of the system, who are the users of the system, and how many users are expected to use it. What components do we need in our design? For example, if you are developing a new social media platform, at the very least, you will need a server to handle user requests and databases to store information about millions of users from all around the world. Next, how these components should be organized and connected to work together effectively. How to make the system scalable so that it can handle more users and requests as needed. How to make the system reliable so if one party stops working, it doesn't break the whole system. And how to make the system easy to maintain and update over time. The fastest way to get good at system design is to learn the fundamental concepts. I've divided these fundamental concepts into 2 buckets: key concepts and building blocks. To keep this video short, I will go over these concepts quickly, but I will share resources you can use to learn them in more detail. Let's start with key concepts. Understanding key concepts will help you to design systems that meet specific requirements. You will also have to make informed decisions about which components to include in your design. Here are the 12 concepts you should know. Scalability. Scalability means how well a system can handle more users or data without slowing down. There are 2 primary ways a system can be scaled: vertical scaling and horizontal scaling. Vertical scaling is when you add more resources to a single scene, like getting a bigger hard drive or more memory. And horizontal scaling is when you add more machines to a system to spread the load. Performance. Performance means how fast your system works. If the system is slow, users can be frustrated. These limits the performance, latency, and throughput. Latency is the time it takes for a single task, and throughput is how many tasks your system can handle in a certain time. Availability. Availability means making sure your system is up and done when users need it without significant downtime. Reliability. Reliability means the system is doing what it's supposed to do, even if things go wrong. The system can be more reliable to matters such as replication, redundancy, and failover intelligence. Consistency. Consistency ensures that all users see the same data at the same time, no matter which part of the system they derive it. But having strong consistency comes with a cost. It can sometimes slow down performance. That's why many systems have improve consistency, but the data may not be updated immediately, but immediately after a specific time. Capture. The capture means that in a distributed system, you only have 2 out of these 3 things: consistency, availability, and partition tolerance. In practice, you need to make trade-offs based on what the system uses the most. Data storage and retrieval. It involves choosing the right database, design the database schema, and using technologies like partitioning, sorting, and replication for optimal storage and retrieval. Basic concepts. Basic stands for complexity, consistency, isolation, and availability. It's a way to make sure that everything we do in a database is done right and reliably. Persistent hasing. Persistent hasing is a method used to spread data across a group of servers. This method makes it easier to add or remove servers without calling too many instructions. It also helps improve load balancing and scalability. Retrievability. Retrievability technique used to control the rate at which lines can make requests to a system. It helps prevent abuse, protect against DDoS attacks, and ensure failures of resources. Networking and communication. This is about understanding how different parts of the system communicate. This involves understanding things like network protocols, APIs, message queues, and even architectures. Security and privacy. Security and privacy means putting in place methods to keep important data safe and stop unwanted access. This involves things like authentication, authorization, and encryption. After understanding key concepts, we start learning the building blocks of system design. Building blocks are different components you use while designing a system. Here are the 8 most common building blocks in system design. Application servers. Application servers are computers that handle the business logic and processing required by the application. Load balancers. Load balancers distribute incoming requests to different servers, so no single server gets overwhelmed. Having websites runs smoothly even when there is a lot of traffic. Databases. Databases is where we store your data. There are different types of databases available to serve different needs. The most common ones are SQL and NoSQL databases. Caching. Caching is a technique used to store frequently accessed data in a fast access storage layer to reduce the load on the primary data. To store frequently ones are SQL and NoSQL databases. Databases available to serve different needs. The most common ones are SQL and NoSQL databases. Caching. Caching is a technique used to store frequently accessed data in a fast access storage layer to reduce the load on the primary data source and improve response times. Message queues. Message queues enable asynchronous communication between system components. They decouple the sender and receiver, allowing them to work independently and at different rates. Storage. Storage systems are used to store and retrieve data such as files, images, and videos. They can be local file systems, distributed file systems, or object storage systems like Amazon S3. Proxy server. A proxy server acts as an intermediary between clients and servers. It can be used for various purposes such as load balancing, caching, security, or content filtering. Serial. Serial stands for content delivery network. It is a group of servers spread across different locations worldwide. It stores copies of website content like images, videos, and files. When you visit a website, the serial serves the content from the nearest server, making the website load faster. Where to learn these concepts in more detail? I put together the best resources to learn these and more system design concepts in this video called Awesome System Design Resources. You can find the link in the description. After going through these articles, you'll have a strong understanding of most important system design concepts. Some of these concepts may seem difficult at first, but if you study them multiple times, it will get easier. If you are interested in learning more about distributed systems, I highly recommend reading this book called Designing Data-Intensive Applications. How to prepare for system design interviews. After understanding the basic concepts, you can start practicing system design interview questions. Once you have practiced a few problems, you will start to recognize patterns such as when to use a certain component and how to think about trade-offs. The system design interviews, many companies tend to ask the same set of questions over and over again. Make sure you practice these 10 most commonly asked questions. There is a high chance that you might face one of these problems in your next system design interview. Design a URL sorting service like TinyURL. Design a social media platform like Twitter or Instagram. Design a chat application like WhatsApp or Slack. Design a web crawler. Design a video streaming service like YouTube or Netflix. Design an e-commerce platform like Amazon. Design a ride-sharing service like Uber or Lyft. Design a notification system. Design a key value store like Redis. Design a scalable login and monitoring system. Where to practice and learn system design interview problems. I would again recommend the different quality elements mentioned here. If you scroll down, you can find many system design interview problems sorted by difficulty level. It contains links to YouTube videos for learning these interview problems. You can start with easy problems and slowly increase the difficulty level. Have linked to the difficulty in the description. Also, it's a good start if you find it valuable. What is expected in a system design interview? Important thing to understand is that you are not expected to be perfect in a system design interview. It is all about trade-offs. And different people make a different approach to solve the same problem. Usually start with something simple and iterate upon it to make it better. The expectation in a system design interview is that you can clarify requirements including personal and non-personal requirements, estimate the capacity of the system you're dealing with, choose the right database and define the schema, design APIs and request response pattern expected from the system, sketch out a high-level diagram and identify major components like databases, servers, clients, load balancers, CDN, gases, message queues, etc. Deep dive into key components and discuss how each part will work when interact with others.
Hey everyone, and welcome back to the channel. So if you read the title of this video, you can pretty clearly see that I am going to be making another systems design series. This one is just going to be for the questions for interviews, and we're just going to go over those. Now the first thing that should be in your head is, wow Jordan, you're a real hypocrite, because this is now like the 3rd time that I've said I'm not going to do this again, and proceeding to do it again. So I guess I should probably go into why that is. I think the 1.0 series, I had 0 visual aids, and I don't think it was in nearly enough detail, and I don't think that I knew enough to really be talking through those questions in depth despite doing it. In the 2.0 series, I still don't think I knew enough, and I probably went into too much depth and over-engineered a bunch of stuff, and I think that rubbed a lot of people the wrong way on the internet. And now, I still don't really know enough, but I'm still getting better and better, and I think I'm also getting more accustomed to how people want to be learning, looking at other resources on the internet, and I'm going to try and put my content in a format that is more amenable to the learning of others, so that they can get maximum utility out of it, while also hopefully still applying some of the knowledge that I've gotten to pick up through some of these deep dives over the last, 6 months to a year. Because I think that's really going to help kind of augment the series a little bit and give people the opportunity to go a little bit further if they want to do so. As always, all of this stuff is going to be free to watch, and it's totally my goal that I want the videos that I post on the internet for free to be better resources for people than ones that people are charging hundreds if not thousands of dollars for. That's what's really important to me. Hello everybody and welcome back. Today I'm excited to introduce the first episode of the Systems Design 3.0 question series. While I spend a lot of time on this channel talking about tiny things, today we will just be talking about tiny URL, not my chode. So let's go ahead and get into it. I'm trying out a new format today. Please give me all the feedback that you want in the comments section. I tried to incorporate literally years of feedback that I've gotten from a lot of people to make this as clear and concise as possible. I don't want to go overboard, but I will explain things as we go, and please bear with me. Let's get into it. For this video, we're going to stick with the minimum possible set of requirements for a service like tinyURL. In practice, this means we need to support two features. First, we need to be able to have a client provide a URL and then pass them back a short URL. These returned short URLs can be configured with an expiration time, after which point they can be reused with another long URL. Next, if another client provides us with a given short URL, we need to be able to redirect them to the original longer URL that it maps to. Notably, we will not cover a couple of other problems, which we will leave for subsequent videos. The first is going to be the paste bin type of functionality, in which we allow users to provide long text content to store, as opposed to URLs. The latter is actually
shared with you a roadmap on how to become a data engineer, and honestly I didn't expect the reaction it got. Many of you followed the roadmap step by step, and even some shared with us.
Data engineer is one of the highest paying data roles, with relatively low competition and a great future. But what does a data engineer actually do? The simple answer is that they design, build, and maintain the infrastructure for collecting, storing, and analyzing data, ensuring it's accessible, reliable, and optimized for performance. But this is a very broad explanation, so let's get into the details of what a data engineer would do day to day. The responsibilities you may have, the exact skills you need, how much data engineers make, and finally, I'll compare the data engineer to other data roles, because that is going to give you a complete understanding of this role when you understand how a data engineer interacts with other data roles in a team. Let's get started. A data engineer might start the day by monitoring and checking the health and operating of different data pipelines and databases, because
Today we're diving. So it can be overwhelming when you.
What is going on, guys? Welcome back to another video with me, Ben Rogashan, aka The Seattle. What is going on, guys? Welcome back to another video with me, Ben Rogashan, aka The Seattle Data Guy. Today we're going to answer the question, what is a data pipeline? And if you're Vicky Boykus, your answer would be, a data pipeline is anything people outside of your team message you about if it's broken. You know, that's not far from the truth. If you're used to being a data engineer, for some reason when anything breaks, it seems to be your fault. But seriously, I did ask a few other data engineers, as well as ML engineers, what they considered a data pipeline, and here were some of their responses.
So data comes in, then something happens with this data inside the pipe, and then it goes out. So this is a data pipeline. So you can think of this as a box. And I don't know if people will watch this or listen to this, so I can try drawing this. So let's say there is a big square, and then something goes in the pipeline and something goes out. So this could be a pipeline, right?
Yeah.
For example, like it could be one input, multiple outputs, could be two inputs, one output, right? And then the nice thing about data pipelines is you can take this single step, right? And then you can chain it.
We have probably all done it. We have probably all assumed that the people we're talking to understands the words and terms that we're using that might be very specific to whatever role we have at a company, even if it's their first day on the job. Again, I think we're all guilty of doing this. So I want to put together a video for people who are just starting out in the industry, or maybe are just trying to understand what their data engineers are talking about by putting together a kind of core set of vocabulary that a lot of data engineers tend to use. To kick this off, let's use the term DAG, D-A-G, or Directed Acyclic Graph. Basically, this is often an abstraction of tasks that need to happen in a certain series of steps. That's kind of the whole point. The directed point, the word basically means that there are multiple tasks, some of which are like going to be upstream and some downstream, so it's going to go in a certain direction. Acyclic just refers to the fact that the DAG itself, or the tasks that need to occur, can't or will only take on one cycle, so it won't like ever get into an infinite loop. And the graph in this case represents that there's a finite set of nodes and vertices that all kind of connect to each other, those nodes essentially being tasks. Basically, it ends up looking kind of like this. So often you'll have something like a task A or first task, but then task B depends on, and maybe C and D depend on B, but C and D can both happen at the same time, and then maybe both of those tasks go into, something like task E to kind of finish it off. So it's a very basic and simplistic graph of basically tasks. It's just basically a chart of tasks that go from A to E. And when someone references the term DAG, that's what they're referencing, a set of tasks that need to occur in a certain order. And in the data engineering context, when we use the term DAG, we're often also kind of connecting to the concept of a data pipeline, which will be the next word we're kind of pointing to. The interesting thing to me about data pipeline is it can honestly cover a lot of different things. There's a lot of different ways we use and design data pipelines. There are the more standard data pipelines, often referred to as like batch data pipelines, which occur at certain time intervals and often follow a pattern of either ETL or ELT, which just references extract, transform, load, or extract, load, transform. And these are just your kind of standard ingestion pipelines, which will often just take data from sources and then push it into an analytical storage system, which we will get to later. And that's kind of your standard set of data pipelines. But on top of that, you also have streaming data pipelines, which often push events directly into often your analytical storage system, or one of those could be a data lake, could be a data warehouse, which we'll get to. But there's also, to me personally, integration pipelines that are often managed by things like iPaaS systems, which iPaaS, or IPaaS, stands for Integration Platform as a Service. So these kind of data pipelines tend to integrate across multiple systems. So whereas your kind of standard ETL will just end up pushing data from source systems like Salesforce or HubSpot into your either data lake or data warehouse, an iPaaS or an integration style data pipeline often integrates two different source systems together. So maybe you want to pull data from Salesforce and integrate it with HubSpot, and then those often connect. These pipelines, data engineers don't generally develop too often. These are more, I think, the work that's either done by like enterprise engineers or, someone who is a Salesforce expert. Because unlike ingesting data and storing it into a data warehouse, you need to understand how the underlying system actually works. So if you're pulling data, let's say from HubSpot to Salesforce, you actually need to understand what's happening in Salesforce. And there's a lot of people who are Salesforce admins and Salesforce experts and developers who understand that kind of work. And so they often, I think, are either involved or just the ones who develop those kinds of pipelines. And look at that, I've unavoidably added iPaaS, ETL, and ELT along with my data pipeline terminology here, because that's just how it ends up working. When we end up having a conversation in any field, it's almost hard not to bring in other terms that we rely on while you're trying to describe the current term you're working with. So that's the interesting thing to me about data pipelines, is it can honestly mean a lot of different things, from more standard batch data pipelines, which usually are, again, ETL and ELT based. And there's even some other things you could add in there as well, to streaming, to some things that are more integration based, where you're just trying to integrate data across different systems. Now, often these more standard data pipelines are utilized in such a way to extract data from some sort of source system, like Salesforce, and then push it into an analytical storage system like a data lake, data warehouse, or data lakehouse. So now you've got even more new terms. So let's start with the classic data warehouse, which is just basically a place to store your kind of company's information in a way that, first of all, attempts to integrate all of your various entities. So you might have your finance data, you might have hiring data, and you try to create some sort of model in that data warehouse that represents your business, essentially. It tries to replicate a lot of everything that you're doing in such a way that, one, it tracks historical information, which is one of the key things, and two, it tries to integrate all that data across all of these complex systems. So that way, when I ask a question that maybe involves multiple departments, I can answer that question because I can connect all this data together. And the fact that it actually tracks historical information, unlike often a lot of source systems, means that when I ask a question that wants to go back over years, you can actually do that. You can select data using something we call slowly changing dimensions, often in such a way to actually look at data from a historical point of view, which we'll get to what we often also reference as SCD here in a second. But first, let's jump into a data lake. Obviously, I'm not going in crazy depth in terms of explaining exactly what a data warehouse is. But one thing I didn't explain there was that data warehouses tend to have a pretty rigid schema that is predefined when you start. And thus, the data types that are required and used in a data warehouse are limited. Whereas a data lake is often more of a place that you can start storing raw data. Often it might be schemaless when you store it, and you might do something that we often reference as schema on read, which is define kind of the schema as you're processing data in the data lake. And it's a place where you can often store data that maybe isn't as naturally fitting into your data warehouse, or maybe it's just too expensive to store in your data warehouse in a more traditional way. It could also be things like images, text that is maybe a little more free-formatted, XML, JSON, just again, things that are maybe less structured or semi-structured is often what we reference. And that's something that often fits into the data lake. There are multiple reasons why people might store data in a data lake or a data warehouse. Some of the things have to do with cost, again, size of the data, or maybe time. Like maybe you don't have time to figure out if this data belongs in the data warehouse, or if you even can provide value, or how to model it or properly fit in. And so you might end up storing it in the data lake as a place that can kind of do some work on it. You might provide data scientists or someone the ability to access it and work with it in such a way that often requires a little bit more of a technical know-how, because you have to do some either sort of coding or work with it in such a way that's not SQL friendly like you would in often the data warehouse, unless of course you put something like Hive or Presto on top. But, there's definitely a lot of nuances to this, and I'm again speeding over this to just help most people understand what a data lake is from high up above. But that's generally a data lake. It's often data that's semi-structured to maybe even not structured at all, that people can store in such a way that should be organized. Try not to make a data swamp, as many of us describe, but can be utilized for future use. Now let's dig into a data warehouse, because there's a lot of different things you're gonna hear the first time you've ever worked in a data warehouse. Like the first time I ever worked in a data warehouse, I didn't even realize it was a different thing, like in terms of like database versus data warehouse. I learned relational models, and so when I was kind of working in the data warehouse, I was like, okay, there's some things called facts, some things called dimensions, but there's like keys, and keys are like IDs, and so you can connect that way. And a lot of it, I just didn't understand that it was a totally different system. So let's kind of dive into some of the different key components you're gonna hear. Starting with some of the tables. You're gonna hear tables that are often referenced as dimensions. Dimensions are generally more like categories or descriptors. Things like product might be a dimension, person or customer is also generally a dimension. You also might have things like category, and actually even date plays a role in terms of dimension, because this tends to describe things like interactions or sales. And those sales, like total sales, are often what we reference as facts. Facts generally are things that involve business transactions, and then everything around that used to basically describe that business transaction is generally the dimension. So think like location. Another way to think about this is, generally speaking, a lot of times when you're creating a pivot table, a lot of things that you're going to pivot on are generally dimensions, right? Because most of the times it's going to ask for the average sales by location and maybe quarter. So in this case, location and quarter are both dimensions, and the total sale end is a summed up version of what would often be data coming from a fact table, those sales numbers or the amount that was sold. So that's often what people are referencing when they say fact or dimension. They're just different types of tables, and often you're going to be querying around the fact table because that's a table that's going to tell you the numbers that you're trying to calculate. Now, in that, there's also something that I referenced earlier, remember, slowly changing dimensions, or often as we just call it, SCD. And these are thrilling things that basically allow you to track historical data. The problem with a lot of source systems is they don't often track historical data. Sometimes they do in logs, and that's why we have things like change data capture, kind of pull in and track every change that occurs in the data system. But slowly changing dimensions allows data warehouses to track like changing dimensions over time using different methods. You'll hear a lot of different ways that people can do this. Like you'll hear someone say like, oh, we're using SCD2 or SCD6, and these are just different ways to kind of capture historical information. And let me give you some context around this. Let's say you're going to create a report and you want to count the number of customers in New York City over the last 3 years. Well, over the last 3 years, people have moved. And if you just pull that data out and replace where someone currently lives in your data warehouse, they lived in New York and now they moved to Connecticut, or maybe they lived in California and now moved to New York. When you run that query, and especially when you do that over time, if you haven't tracked that historical information over time, you're going to give the wrong numbers because whatever
Today we're diving into the world of data pipelines. So what exactly is data pipeline? In today's data-driven world, companies collect massive amounts of data from various sources. This data is critical for making informed business decisions and driving innovation. However, raw data is often messy, unstructured, and stored in different formats across multiple systems. Data pipelines automate the process of collecting, transforming, and delivering data to make it usable and valuable. Data pipelines come in many different forms. The term is broad and covers any process of moving a large amount of data from one place to another. We present here is a general version of it, but this is by no means the only way to implement an effective data pipeline. Broadly speaking, a data pipeline has these stages: collect, ingest, store, compute, and consume. The order of these stages can switch based on the type of data, but they generally have them. Let's start at the top with data collection. Imagine we're working for an e-commerce giant like Amazon. We get data flowing in from multiple sources: data stores, data streams, and applications. Data stores are databases like MySQL, Postgres, or DynamoDB, where transaction records are stored. For instance, every user registration, order, and payment transaction goes to these databases. Data streams capture live data feeds in real time. Think of tracking user clicks and searches as they happen using tools like Apache Kafka or Amazon Kinesis, or data coming in from IoT devices. With all these diverse data sources, the next stage is the ingest phase, where data gets loaded into the data pipeline environment. Depending on the type of data, it could be loaded directly into the processing pipeline or into an intermediate event queue. Tools like Apache Kafka or Amazon Kinesis are commonly used for real-time data streaming. Data from databases is often ingested through batch processing or change data capture tools. After ingesting, the data may be processed immediately or stored first, depending on the specific use cases. Here, it makes sense to explain two broad categories of processing: batch processing and stream processing. Batch processing involves processing large volumes of data at scheduled intervals. Apache Spark, with its distributed computing capabilities, is key here. Other popular batch processing tools include Apache Hadoop MapReduce and Apache Hive. For instance, Spark jobs can be configured to run nightly to aggregate daily sales data. Stream processing handles real-time data. Tools like Apache Flink, Google Cloud Dataflow, Apache Storm, or Apache Xamsa process data as it arrives. For example, Flink can be used to detect fraudulent transactions in real time by analyzing transaction streams and applying complex event processing rules. Stream processing typically processes data directly from the data sources, data stores, data streams, and applications, rather than tapping into the data lake. ETL or ELT processes are also critical to the compute phase. ETL tools like Apache Airflow and AWS Glue orchestrate data loading, ensuring transformations like data cleaning, normalization, and enrichment are applied before data is loaded into the storage layer. This is the stage where messy, unstructured, and inconsistently formatted data is transformed into a clean, structured format suitable for analysis. After processing, data flows into the storage phase. Here, we have several options.
I was learning.
Welcome to another
Today, we're diving into the world of data pipeline.
What is? Hello friends.
Once
Let's talk more about data modeling. Let's talk more about data modeling. In particular, if you saw the...
Hey y'all.
Let's talk...
Data modeling is one of.
Let's talk more about data modeling. In particular, if you saw the last video, we mostly focused on your standard concepts in data modeling, normalization, denormalization. Data engineering. What's going on, guys? Welcome back to another video with me, Ben Rojan, aka the Seattle Data Guy. Today we're going to do something that I've been meaning to do for a very long time, which is actually finish a data engineering project for you guys. Now we're going to be restarting all over again, but I already have a very straightforward plan in terms of what this project is going to be. I'm going to outline it here shortly, but let's talk about it. So let's start with the data source. The data source for this project will be Predicted's data source, which for those of you who don't know what Predicted is, it's basically a marketplace that you can kind of essentially bet on political things, like who will be the presidential nominee in 2024 for the Democrats, which let's talk more about data modeling. In particular, if you saw the last video, we mostly focused on your standard concepts in data modeling, normalization, denormalization, and a few other just key concepts. But it really ranged from traditional, relational databases to data warehousing. So it wasn't very pointed at the kind of data modeling we do as data engineers, which is important to point out that obviously data modeling, again, goes both for the operational, otherwise known as transactional side, as well as the analytical side of your data. So today, let's talk about the analytical side. In particular, we're going to focus on a few key things. First, a review, if you have by chance not had a chance to, of the key tables that you will likely see. We'll just cover a few of them. There's honestly plenty more, but we're just going to cover the key ones for today. We'll go over a few of the scenarios you'll likely end up in terms of decisions you have to make, and then we'll go through an example that is put out by Kimball in his data warehousing toolkit, which honestly, a lot of people ask for examples. There's like a dozen in his both books and some of his online content. You can find a few good examples of how you can develop your own data model. So let's just jump into it and talk about some of the key tables in data warehousing, and more specifically in dimensional modeling, since that's where we're really going to focus on. So obviously there's plenty of tables here. We're really just going to talk about facts, dimensions, bridge tables, as snapshots. And then again, this will be a good refresher for some of you, and if not, if this is new, it's really good information to know. So if you look at your traditional data warehouse, you'll generally see a few facts and a lot of dimension tables. This is because the fact tables, if you look at what they represent, generally are the, at least pulling from the data warehouse toolkit, primary table, essentially in the dimensional model, where the numerical performance measurements of the business are stored. Basically, these tables contain often the quantitative data that represent the transactions, events that occur in a business or organization. And I say organization because this isn't just your sales fact table or your fact sales table. There's also the opportunity or option that you might have a grade table or an assignment table. If you're some sort of education system, you might actually include a different type of fact table that has nothing to do with the business transactions, but more to do with organization. You can call it a business, but I'm sure some people would like to delineate the two. The point is, these tables generally are the tables that have the events that you're going to be aggregating and summing on, doing division. Again, there's other types of fact tables that we're not going to talk about today that you'll get into issues if you do that. But in this case, the plain vanilla old fact table is the table you're going to likely answer all of your questions from, right? Like it's all the numbers, everything there is going to be able to be aggregated, sliced, diced, etc. You're going to be able to basically find data, things like how much you sold product for, again, maybe what grade someone got for an assignment, how much inventory is left essentially in your warehouse, or how much inventory was essentially moved outside of your warehouse at a certain point. Or maybe if you've got like an invoice fact table, which we'll talk a little bit about here in a second, the line items and how much people pay per thing, and the quantity per thing that you're actually paying for. And so again, it's all of these like numeric things. And so this is kind of a good example here of a fact table. You'll see a lot of keys that will point out to the dimension tables, and then a few specific quantitative values. And then that brings up obviously the dimension table. And if you're an analyst, the easiest way to think about them is that these tend to be the tables that have the information that you often slice and dice by. And when I say that, I mean like when your leadership asks you a question, they often ask you, how are sales going for this quarter? I would love to see your report quarter over quarter, broken down by region, and maybe sales representative. So in this, you have the fact, which is sales, so how much money was actually sold per region and quarter, etc., and the dimension, which were all those other things that I referenced. The quarter, which is date and time. You have things like region, which is a very common dimension to work off of some sort of location. And then finally, sales representative, so a person or something similar might break that down. You might also have things like departments, accounts. There's a ton of different things that could be here where someone generally wants to slice and dice this data by. They are the dimensions. In again, Kimball's book, he calls dimensions attributes that essentially serve as the primary source of query constraints, groupings, and report labels. In a query or report request, attributes are identified as by words. Attributes are identified as the by words. For example, when a user states that he or she wants to see dollar sales by week, by brand, week, and in turn, brand must be available essentially as an attribute. So again, there are these other pieces of information.
Engineering technique for training machine learning models. I'll explain how to do that in Python code. We are doing this in a co-op notebook, so take a look in the video description if you want to follow along with that. But either way, we've got 1, dimensionality reduction using PCA, 2,
Everyone.
this end-to-end. Hey guys, it's Greg. Welcome back.
Feature engineering, data transformations, ETL, data pipelines. If you've ever heard these terms and wondered what the heck they were, this video is for you. So if you put 10 data scientists in a room and ask them to define data science, you wouldn't get 10 answers, you would probably get 20 or something. And there's a lot of reasons for that. Mainly where data science is a interdisciplinary field, and data scientists, we all come from very, very different backgrounds. For example, somebody that comes from an economics or statistics background like myself, social sciences, is going to look at things and solve problems a little bit differently than somebody that comes to the field from, like, let's say, computer science or engineering. But in general, this is kind of how I think of data science, or how I would define it to people. Is, and again, maybe not everybody's going to agree with this, but I think most would. We take raw information that exists in the world, and from that information, we generate actionable insights. So there's several different steps to getting from raw information to actionable insights. You're probably all familiar with modeling and building an AI model. I mean, that's certainly something that data scientists spend a lot of time doing. Also deployment, getting it consumable, and then actually getting the insights from the model. Once it's deployed, that's kind of the whole point. But one part that I don't think gets quite the attention that it deserves is this part right here, going from raw information to transformed information. And this is what we call feature engineering. And again, sometimes it's called data pipelines, sometimes it's called ETL, sometimes it's called variable transformation. Data transformation, but those things might mean something different in other contexts. But in the context of data science, they all pretty much mean the same thing. It's the process of taking raw information as it exists in the world and transforming it into in a way that it maximizes your AI model's ability to predict. So what does feature engineering look like? What kind of feature engineering would a data scientist do? Probably the most common one is something that we call dummy variables, or sometimes it's called one-hot encoding. But this is a situation where you have a variable that is a category. For example, yes,
no, yes, forms like that. Text like this or category like this, a lot of times the AI model doesn't really know what to do with it. Of course, it depends on the model, but a lot of the models that we use really can't handle text information. So one way that we'll transform it so that it's usable by an AI model is we create these things called dummy variables. And a dummy variable is just taking one column of data and splitting it into multiple columns. So the original variable was yes. So the new column we've labeled yes is going to be 1.
Hey guys, it's Greg. Welcome back. Today Hey guys, it's Greg. Welcome back. Today we have an awesome video. Pretty much every feature engineering technique for training machine learning models. I'll explain how to do that in Python code. We are doing this in a collab notebook, so take a look in the video description if you want to follow along with that. But either way, we've got 1. Dimensionality reduction using PCA. 2. Reprocessing and scaling methods. 3. Categorical encoding, so dummy and 1 hot variables. 4. We've got binning, grouping, aggregating features together. 5. Clustering, so here's the map of California. For example, we can cluster the latitude and longitude and get this kind of pretty picture out of it. It doesn't have to be that geographical data, but that makes the most sense visually. And finally, we've got feature selection, combining all of this different stuff together and only taking what you want to. Okay? If you only want to learn one or a particular subset of these ideas, I do have marked in the chapters down below on all these different topics, so just go and learn what it is that you want to learn. Or if you want to follow everything along with me, I've got it here at the start with initial setup. But before you go off and do your own thing with this video, visually. And finally, we've got feature selection, combining all of this different stuff together and only taking what you want to. Okay? If you only want to learn one.
If you made a neural network on the surface of Mars, you'd be a long, long way away. If you made a neural network on the surface of Mars, you'd be a long, long way away from me. That's the truth. StatQuest. Hello, I'm Josh Starman. Welcome to